everybody. We're going to do a very important reaction now. The synthesis of epoxide. What is an epoxide, you ask? An epoxide is a triangular ether. So when you have an epoxide, you've got this as your minimum. Well, that's not a very good triangle, is it? Epoxide has 2 carbons and an oxygen as a bare minimum. We use epoxides for synthesis in Orgo 2 on every test, starting with the first one. And you're going to use it on your test or your final exam too. So we have to know how to make them so we can use them later. And we're making them. Notice I'm making the same epoxide by 2 different methods here. This is the cheaper method. This is the faster method. So if you want to make money, you always use the cheaper method and you pay people to spend the time to make sure it works. Faster methods when I need that epoxide yesterday. Okay, so this is just vicinal halohydrin forming. Vicinal halohydrin, chapter 6, 6.1. Oh, I'm going to hazard a guess that it's, I don't even know, D, E, F, something. It's early on, 6.1. And you got to remember, water reacts with bromine first to make bromine water. So this is one where the water is the solvent and it is a reactant too. Here it's reacting for the first time. And it's attached to, wow. H2O is now attached to a Br, which has 3 lone pairs, but I need one of them. And Br minus, really not that important. Small and off to the side. And this was one of our early triangles. Remember that? Triangle time? We attack the Br with the pi. Water gets booted off. And instead of a carbocation, lone pair comes back to that carbon to make a triangle. And now we're talking about these 2 becoming this. Let's go with purple. And let's put the Br on a wedge. Why not? 2 wedges. And don't forget, those are real bonds in this triangle because we use 2 arrows to make those. That's real bonds. And don't forget, bromine now has a plus. And you also made water. Not that you need this particular water. Any of the waters that are floating around, the solvent, going to do a backside attack on which carbon? More substituted, because that's the one that spends more time with a plus charge. And plus charge is clearly important here, right? And backside attack. Bromine leaves, but not quite because it's got 2 bonds. And purple. Bless you. And water, backside of a wedge would be a dash. Oxonium. We've had hundreds of oxoniums this semester, and we know how to make oxoniums into their conjugate bases. Water is being used the 3rd time. Yeah, water's getting a workout here. Slightly better base than Br minus, and there's a very large excess of it is the reason why water is the better base for this choice, so for this acid-base reaction. So nothing was new there. That's a review reaction. But I'm putting it here because this is a nice way to make epoxide. What you can do on the test, if you need to show a bond from O to H breaking, you can just scribble out the H and draw the bond, scribble out the spectator, and do your acid-base step, because you need to do that right here. Yeah, that isopropyl's kind of in behind. I hope you know that. And then we got this. We're almost there for this one. And you got a O minus, which is a nucleophile, in the same molecule where there's a leaving group. Oh, wait, this sounds familiar too. Yeah, it's like an NGP, well, and like only half of it. We're just doing the NGP part without doing the other nucleophile following it. Because this triangle we're making here, I know it's a triangle, it's not happy. But it's got bonds to oxygen, which are nice, strong bonds. So this triangle is the end of the story. And I saw your hand there. And yeah, we're making this triangle, which is not usually a great thing, right? Usually you'll see it pop open. But epoxide triangles, yes, reactive, but we can isolate them and store them and use them later. For a triangle, they're pretty stable. But they're still a triangle. You can do things with them. Our last activity today, we're going to show you the two main uses of these epoxides. And by far, making epoxides and then using them in Chapter 11 is the important thing. The important thing. So the things today are, we're done with the most important things of the semester after today. Everything else is like tidbits. So I really want you to hit that final exam review, and any multiple choice questions you see that I don't think we covered these, Dr. Whitaker, please bring those to class Monday. We'll do them together, okay? That'll be a good use of Monday. And that's method of making epoxides number 1. You're gonna love the next one. You don't have to, there's a reason why it's all in one little area there. You don't need any more room. This is called a per acid. And its initials are M, C, P, B, A. Meta, chloro, per, benzoic acid. This is a per acid, as its name implies. And what does per mean in chemistry? You saw per iodate ion in Chem 141. We skipped per iodic acid, which we may come to on Monday. I'm still deciding about that. If you bring me the multiple choice question with per iodic acid, we're going to talk about it. What's the per mean always? I like what you're saying, except for carbon. When she said the O fills every bond, I think that covered it when you said just that. You have as many bonds to oxygen as possible for that atom, is what a per is. Okay. So you can't get more bonds to oxygen with this carbon. And it looks like an acid, which it's got a peroxide in the acid, right? So you can remember it that way too. Peroxide is that fills the definition too. It's normal oxide, but an extra oxygen, right? I'm just going to put a note here about the other per acids you need to learn. Others you need to learn. You need to learn. I'll narrow it down to two more. Peracetic acid and this one's tricky. I'm going to give you the initials first. I mean, it's not tricky. Just got a lot of stuff. MMPP. Easy to remember. Double M, double P. Magnesium monoperoxy PHTHALATE. You want to try to pronounce that? It's kind of like we get some weird words in English, and this is one of them. Some letters get said and some don't. Like pneumonia, do you say the P? No. This one, same. Just say the N, phthalate, with a hint of a P at the beginning, a silent P at the beginning. There you go. And what it looks like, if you're curious, magnesium is a cation with a 2+, right? So what happens is you get two of these anions. Phthalates are benzoic acid with 2 carboxylic acids. This one's got one of them is a per. And there you go. Why so complicated? Well, it's not that it's so complicated. It's that this one is the most stable on the shelf. Okay? If I'm going to put the minus here, I better put 2+ here. Just to be consistent. That's your normal magnesium there. The other ones are dangerous. MCPBA, you can't keep on the shelf long because eventually it's going to ignite or explode. And peracetic acid, you basically have to make it and use it immediately. It's not a nice one. This one, you can keep for years. It's a nice one. Anyway, all that talk, we just got to learn the mechanism. It's got 4 arrows. And just remember this. The first arrow, once you get the first arrow, they all flow from it, okay? The first arrow attacks the oxygen that is distal to the carbonyl, as opposed to proximal. I'm using some nice biology lingo here, right? Distal's further away, proximal, as it implies, is close. So which of these two O's is distal to the carbonyl? That one, yeah, the one with the H, exactly. So you attack that with the pi electron. Attack the one that's further from the carbonyl, and then watch the flow of electrons. It's nice. The sigma here becomes a pi. And the peroxide problem is gone. With that OO bond is now gone. We don't like OO. Then the carbonyl O protonates. And the 4th arrow, I'm going to do in a different color. I don't know why. You don't have to. How about baby blue? Goes to which carbon? It's been the same answer all semester, right? The one that spends more time with a plus charge, the more substituted carbon. Now in the book, you'll see the arrows are numbered. You don't have to number them. You don't have to have different colors. In fact, I'll just make that red right now. Didn't have to be 2 colors. So this says O makes a bond to this carbon. This says carbon makes a bond to the oxygen. And this says the O on top is going to become an OH, look. And this says the O underneath is going to become a carbonyl, and it covers everything, right? No intermediates at all. I love that mechanism. And that's all you need to know about the per acid. Well, you have to know the 3 per acids, MCPBA, peracetic, here's peracetic since I drew the other one. Let's not show favoritism. There's acetic acid, there's peracetic acid right there. And my C looks like another O, sorry. Do some trim in there. Worked out. And we have to know MMPP. Boxes here. There you go. And that's activity 3. There you go.